Welcome. Good morning. Today we discuss model adequacy tests and factor rotation. Under model adequacy test, you will see Bartlett's sphericity test, large sample likelihood ratio test. Then we discuss number of factors to be retained, factor rotation, orthogonal as well as oblique rotation. Let us go to the next slide.
We will continue factor analysis. We have described the conceptual model and we have given some examples, and in second lecture we discussed about the model estimations, that is from principal component analysis point of view, from principal factor method point of view, and also we have discussed discussed about the maximum likelihood method point of view. This lecture will start with model adequacy test. Model adequacy test, then followed by your factor rotation, followed by factor scores. Then I will show you SPSS, exploratory factor analysis, and if time permits I will go for confirmatory factor analysis. That only basics. Okay. So, under model adequacy test, I have already discussed the correlation matrix, and I said that if there are substantial correlation coefficients greater than equal to 0.30, then you go for factor analysis. Means suppose you have a large data matrix and the correlation coefficient matrix is P cross P, there are large number of values having more than 0.3. Second is Bartlett sphericity test. Bartlett sphericity test uses this formulation, that you find out the correlation matrix first, take the determinant of it and take logarithm of this, then you multiply with this, this ultimately follows chi-square distributions with p into p minus 1 by 2 degrees of freedom. Now, if this quantity is more than the tabulated value, then the null hypothesis that there no factorization possible, that factor analysis is not possible, that is not true here. Okay. So, we will reject null hypothesis in this case. Then another one is that large sample test, which is likelihood ratio test, large sample likelihood ratio test. So, we will again give you the Bartlett procedure here. Here the null hypothesis is that the population covariance matrix is coming from the factor model. I mean, we are able to reproduce from the factor model this population covariance matrix. It is correct. And H1 is that sigma is any other positive definite matrix. Okay. So, this is my step 1, that means set the hypothesis. Your step 2, you have to find out the statistics, appropriate state statistics. What is your state statistics? As I told you that it is the log likelihood ratio. So, minus 2 log this capital lambda, this lambda is not this capital lambda. So, In this case, this is basically similar to this Wilks lambda what you have seen earlier, that similar to that Wilks lambda type of things. So, if I write like the not lambda here, if I write that this is our, let it be W. So, we are creating this, and that one is minus 2 log determinant of that sigma cap by determinant of Sn, where Sn is n minus 1 by n into S, that is the sample covariance matrix. For n greater than very large tends to infinity, then Sn become S. So, for large sample size you can use S determinant here, determinant of S. Okay. Then once I know, so that means what is my state statistics here? My state statistics is minus 2 log determinant of sigma by determinant of Sn. Then you have to find out that what is the sampling distribution of the state statistics. Now, Bartlett says that m log determinant of sigma by Sn. So, please keep in mind that we are writing the estimate value here sigma. This one, because this is what is our random variable, random component here. So, this follows chi-square distribution with half of p minus m square minus p plus m, that degrees of freedom. So, first this hypothesis related to the population, then sample statistics related to the estimates, then your sampling distribution related to the estimate. Now, you have to take the decision. Decision will be reject H0 if this quantity, if I write this total quantity as D, so if D greater than equal to chi square half p minus 1 square minus p plus m, that alpha, for maybe usually alpha we take 0.0. So, if you reject H0 for this condition, what does it mean? You are saying no, it is not, that the factor model is not able to reproduce the population covariance matrix. So, if you want to have your factor model acceptable, then H0 should be accepted. Okay. So, this is from the hypothesis testing point of view, correlation matrix, Bartlett test, all those things we have discussed. So, next issue is that number of factors to be written. How many factors you will keep? So, it is similar to principal component analysis, where we have seen that number of component to be kept by several means. For example, percentage cumulative variance explained, then your we have also given you eigenvalue criteria. So, how much? It may be eigenvalue criteria when you use R matrix, then scree plot is there, similar things. Okay, similar many things we have explained there. For example, let we have p variables, you have extracted, let it be 3 factors. and you know the loadings. Okay. If I say, then you know the eigenvalues here. This is 2j, 3j, 3j, j equal to 1 to p, that square. So, you find out the percentage, what percentage it is, what percentage it is, what percentage it is. Then you find out the cumulative percentage. Set a criterion, let you want the cumulative percentage, it should be greater than equal to 90%. Are these three factors you are considering able to explain this? If yes, this factor model is good and you can keep three factors. Okay. Now, scree plot also you have seen earlier. Your scree plot, what we have seen, that this eigenvalues vis-a-vis factor 1, factor 2 like this, eigenvalues, suppose your values are coming like this. So, this is your elbow, so you keep three factors. An eigenvalue when you use R matrix, so for those eigenvalues which are more than 1, that you consider at least 1, and at least one variability will be explained by this. Okay. This is similar to principal component analysis, how to keep the how many components you want to keep. Okay. As we have discussed earlier, factor analysis has two important purposes. What are those two? One is your definitely dimension reduction, second one is interpretability. By interpretability we want to mean that we will be able to provide name to each of the factors. Correct. So, how do you provide name? For example, consider that we have three factors here and there are several variables like this, and when you have seen the loadings, that means lambda values, you might have found out a situation similar to this, where these loadings are high with factor 1, these loadings are high with factor 2, these loadings are high with factor 3. But the other loadings like x1, x2, x3 loadings on factor 2 as well as factor 3, they are very small, negligible. That means we can ignore those loadings. Under such situation, what we can say that x1, x2, x3 is creating factor 1, x4, x5 is creating factor 2, x6, x7, x8 is creating factor 3. Then we can probably name these factors considering what are these variables, what is the nature of these variables. The name will be governed through these three for F1, these 2 for F2, these 3 for F3. Can we get this structure? Immediately when we basically conduct exploratory factor analysis the way we have discussed. By any of the method, maybe your principal component analysis method, your principal factor method, your maximum likelihood method, any one of the method, you have extracted factor, estimated the factors, parameters, models are available, are you getting this or not? It may so happen that you will not get this structure. Under such situation, it is desirable to rotate the factor in such a manner that the loading of some of the variables on a particular vector, that F1, that factor, that will be maximum, whereas the loading of other variables will be minimum. Similarly, we want to find out some other set of x excluding the ones we have considered for the F1, that which will be highly loaded with F2 and very low loading with other factors. So, this can be possible through factor rotation. Okay. So, in order to understand this fully, I will first show you one example. See, this is the results obtained by Maxwell-Lawley 1971 paper. They have conducted factor analysis of per responses of 220 students under 6 variables: Gaelic, English, history, arithmetic, algebra and geometry. And the factor loadings, they have extracted 2 factors, factor loadings and then commonalities are like this. Okay. Now, if you see these loadings, Gaelic is equally loaded, almost equally loaded with factor 1 and factor 2, because the loading value is 0.553 for factor 1, 0.429 for factor 2. Similarly, English also definitely English has certain higher loading on factor 1, little lower, but it is not negligible loading. For history, again equal pattern almost. For arithmetic, yes, there is higher loading for factor 1 and definitely from compared to 0.74, 0.27 is less, but none of the loadings here, if you find that, are 0. In that sense, none of the variables are not loaded with the 2 factors considered. Okay. Keep in mind that this negative symbol here given, this is not a issue here. Basically, it may be the negatively loaded or positively loaded, but they are loaded. Okay. So, under this condition, if we want to see the plot of these factor loadings, what we will see? You will see that your this basically for different factors. For example, factor 1 and factor 2, these are the 2 axes. Now, Gaelic 0.553 and 0.429. So, I think 553 somewhere this and 429 somewhere this one. This is the first one. Second, English 5.568 and 0.288, 0.568, 0.28 this value. Then third one is history 0.329, 0.329 and 0.450 is this value. And then arithmetic, algebra, geometry coming under this side. So, if we consider now these two axes, that first one, this one is f1 and f2, that what we have considered, then you find out that for these three, arithmetic, algebra, geometry, almost highly loaded with factor 1 and lowly loaded with factor 2, but you cannot say that with the other, that literature related things like Gaelic, English and history. They are almost at the here this side is okay, that is not highly loaded with the second factor or highly loaded with the first factor. So, under such situation, if I rotate the factor, can we get some better picture? So, if you rotate, you will get this type of picture. Okay, now let us see again this one, and I will draw that how it is possible. So, our case is like this. Case is like this. This is my f1 and this one is f2. Okay. Now, let us do some manipulation. What we can do, we will go for rigid rotation first. So, let us rotate both the axes like this. This is my new f1, then if I do perpendicular here, this is your new f2. I am saying this is star, f1 star and f2 star, f1 star and f2 star. So, this one is rotated clockwise, so this angle is theta. Similarly, this angle is theta. So, if I know theta, then you will be able to find out f1 and f2 star from f1 and f2. Okay. And that is possible. For example, in this curve, suppose this is equal to 20 degree, then I think I have given you in principal component analysis one matrix like this T, which I say cos theta minus sin theta, then sin theta cos theta. That means what I want to say here, f1 transpose is your f1 cos theta minus f2 sin theta, and your f2 that new dimension is f1 sin theta, let it be plus f2 cos theta. Now, this plus minus symbol, this were the here or here, it all depend on the theta value. So, and we also have seen that this one, this T earlier, that if you say that T transpose equal to T transpose T equal to T inverse equal to I, then we say this is orthogonal transformation. Orthogonal transformation. I means, and we have done that because rigid rotation keeping 90 degree intact, we have done this one. Okay, orthogonal transformation. Using this transformation, you got this. Okay, you see now these loadings. Now, if I see the loadings from the arithmetic, algebra, geometry point of view, Okay, this is the case. So, arithmetic, algebra and geology, geometry point of view, you see that in under factor 2, 0.001, 0.054, 0.083, almost 0 loading, but they are very highly loaded with factor 1, 0.789, 0.752 and 0.603 is factor 1. And related to factor 2, now at least what you are able to see that the first 3 variables, they are more, that they are higher loading, they have higher loading with factor 2 in comparison to factor 1. So, this is better picture. So, we can say now that these two factors are basically talking about two things, one related to arithmetic, algebra, geometry, which are basically mathematical ability, and other one Gaelic, English, history, these are all literature based. So, this may be your verbal ability. So, Lawley and Maxwell, they says that this intelligence, that having arithmetic, algebra and geometry, these are mathematical ability and verbal ability. These two component are factors are hidden there, and which are manifested in terms of the performance in the mathematical subjects as well as the literature based subjects. Okay. So, but here another issue is coming up. That issue is, if I go for some other type of rotation which is not orthogonal, then what you will find out, suppose if I do the same, this axis, okay, let it be like this, but the other axis if I rotate like this, I will make this angle less than 90 degree. Then this will be known as oblique rotation. Oblique rotation. I mean, there will be correlation between the two. There will be correlation between the two. Getting me? Now, what we can do, that we want to see under orthogonal transformation, or other way I can say under orthogonal rotation, are we losing anything related to explaining the variability of the original variables. Okay. Let us see this one. What is our covariance structure of the original variable? That is sigma, and we proved that this is nothing but lambda transpose plus psi. Okay. Now, if I create something like this, when we have created this type of transformation, rigid transformation, that f to your f to f star, that is f1 to f1 star, f2 to f2 star. Then what actually happened ultimately? Our model is x minus mu, that we say lambda a plus this is our original model, and from this model you got this structure. Now, instead of this, if I say that f star is nothing but a, that is t and a, tf, because what you are doing here, you are writing f here with some other matrix, this t, f is tf, where t has having this property. Getting me? So, that means my model will change to x minus mu equal to lambda f star plus delta. some other directions. What will happen to this lambda lambda star, sorry, lambda lambda transpose? So you will instead that it is basically lambda will become lambda f is there, so this lambda f will become lambda t f, fine. So then what I can write, you can give some other symbol, then lambda tf, and this side it is coming lambda transpose, that will be f transpose, again t lambda, or lambda if we keep out, don't keep out, just if I say transpose here, f transpose, t transpose and lambda transpose. The resultant matrix, what will happen, this lambda lambda transpose, that will be like this, sigma will come, lambda lambda transpose case, it will be lambda t t transpose lambda transpose plus psi. Resultant thing will come like this once you manipulate in this manner. Now what is T T transpose or T transpose T? T transpose T equal to T T transpose equal to I, even the inverse also I. So this is again lambda lambda transpose plus this. So from covariance structure point of view, there is no problem, you are explaining the same structure, only thing is that your this factor values are changing from f to tf, some other dimension, the loadings are changing. So that means factor loading will not reduce the explanation power, it will keep the same amount of information from the variance explanation point of view, but from interpretability point of view it improves.